Welcome to another episode of Maths in an Empty Classroom with me, Mr. Southern. This lesson is on using differentiation for optimisation problems, and I'm just going to be going through one example of that. So here we have a diagram showing a square card ABCD of side 8 centimetres, that's indicated here. From each of the corners is removed a square of side X, and the remainder is folded along each of the dotted lines to form an open tray of depth X and volume V. And in part A, we're being asked to show that V, the volume, equals 64x minus 32x squared plus 4x cubed. Now, the first thing that I'm going to do is I'm just going to draw out a very quick diagram of what the 3D version of this shape is going to look like. So there we go. That's what the 3D version is going to look like. Now let's consider the dimensions. We are taking x away from each end of the box. So this length here that we're going to be left with in the middle is going to be the original length 8 minus 2x. So that is going to be the length along the base of the shape. We're going to end up with a square base because as well as taking x off this way, we're also taking x off this way, which means that this length here is going to be the same. So it's going to be 8 minus 2x along here as well. And then when I fold this box up, the height of that box is going to be this length here, that gets folded up, so it's going to be a length of x. So those are the dimensions of the cuboid that I'm forming. So to get the volume of this cuboid, I would multiply x by 8 minus 2x by 8 minus 2x, which is what part A is asking us to do. So here we have x, 8 minus 2x, 8 minus 2x. So expanding out, we're going to have x, we're going to have 64, minus 16x, minus another 16x, we're going to have minus 32x, plus 4x squared. This is already looking pretty promising given what I'm supposed to be showing. So expanding that bracket out, 64x minus 32x squared plus 4x cubed. And that is my expression for the volume of the shape, and that is part A done. Okay, part B is asking me to find dv dx, so to differentiate v in terms of x. So what I just need to do is to differentiate a term at a time. It's important with these that we do write the correct value of what's changing, so it isn't dy dx, that might be what you're used to with differentiation, but because the original function is v, we are differentiating v with respect to x, and it's important that we get that right because it has many, many more uses in the second year of A-level maths. 64x is going to differentiate to 64, 32x is going to differentiate to negative 64x, and 4x cubed will differentiate to 12x squared. And that is my expression for dv dx. Is part C done? Part B, I should say, done. Part C is saying, hence find the value of x for which dv dx equals 0. So for part C, here's dv dx. So I'm just going to write it as 12x squared minus 64x plus 64 equals 0. And I need to solve this equation to find the value of x. Now the common factor of 4, so I'm going to divide through to get 3x squared minus 16x plus 16. I'm old school, I'm factorising it, I'm not going to crack the calculator out for this one. So 3x and x, negative 4 equals 0, which gives me the solutions x equals 4 over 3 and x equals 4. So I've actually got two solutions here, but part C said very clearly find the value, a single value of x. So let's just think about which of these two is sensible. x is the amount that you're cutting off the corner of this square. Now if you cut 4 centimetres off this side, and you cut 4 centimetres off this side, you wouldn't have any box left. So x equals 4 is not a valid solution. So we would just proceed with x equals 4 over 3. This is one of those cases where it solves the equation but it doesn't solve the model. So reading the question is very important, and then choosing the sensible answer out of the two. Okay, that's part C. Part D is saying show that this value of x gives a maximum value of v. So a maximum value of v. We have to demonstrate that this is a maximum, and the way that we do that is to use the second derivative. So we know that dv dx is 64 minus 64x plus 12x squared. It's just a pitfall here that we've got to be aware of. We divided this through by 4 to make the equation easier to solve, but this is not an expression for dv dx. We must go back to our original expression for dv dx, not what we manipulated it to solve in part C. So my second derivative of this, I'm just going to differentiate each term of dv dx. So the second derivative of v, I'm going to get negative 64 plus 24x. Now, using my value of x of 4/3, I'm going to evaluate the second derivative by substituting in x is 4/3. So I'm going to get negative 64 plus 24 lots of 4 over 3. And that comes out as negative 32. Now the fact that I've got a negative value for my second derivative means that the value of v is a maximum for that value of x. So I would write that the second derivative is less than 0, therefore v is a maximum. Crucially, it's not x that's the maximum, because x is giving us a value to sub in to find v, and it's v that is the maximum. And part E is saying find the maximum value of v. So in part E, to find the maximum value of v, we need to substitute x equals 4 over 3 into our expression for v, which was 64x. Was it minus 32x squared plus 4x cubed? Yes, it was. Minus 32x squared plus 4x cubed. X equals 4 over 3. So therefore v is 64 lots of 4 over 3 minus 32 lots of 4 over 3 squared plus 4 lots of 4 over 3 cubed. So substitute that in. So thousand and 24 over 27. Right, just check a couple of things. Find the maximum value of v. Lovely, so we're fine. Centimetres was the unit of length, so it's going to be 1024 over 27 centimetres cubed, and that is our value of v. Couple of things to watch out for, just a little bit of exam technique. These questions always start with a little bit of algebraic proof to show that v equals, or h equals, or y equals, whatever it is. And often students think that if they can't do the first bit, they can't do the rest of the question. That's wrong, because you're given the expression for v, you can use that to finish the question. And what I sometimes advise students to do actually is to do parts B, C, D and E first, get those marks, bank them, and then come back to part A and do that last. But it's your call. The other thing that often happens is that you sometimes get part E being asked without part C. So find the maximum value of v. You would have to know that you differentiate, make it equal 0 and solve. What often happens in that case is students get to x equals, and as mathematicians we're conditioned to say, oh, x equals, I must be done, stop, and they forget to sum it in to find v. So just be aware of that when you're practicing similar questions to this by yourself. There we go, job done.